Ooh. Still not fixed? Uh-oh, still not fixed. Not a good sign. Did you guys have same problem for other class?
Yeah, usually they're able to get it to work by jiggling it a little bit on the wall.
All right, let's do it.
Jiggle. I think it's actually the connection at the computer.
Yeah.
Is where the short is.
One right that you plug into.
So, okay, you mean here?
Yeah, it's somewhere around.
Oh!
Yeah.
Start to share it was like.
Oh.
Oh my God. You got.
Will's got the magic touch.
Yes. I'll get them. I'll make sure school should pay for a new cable, right? That makes total sense. Okay.
Welcome to a Cisco meeting. You are entering the meeting now.
Okay, let's get started. Great, we got everything working. The slides looks pretty good. No different colors. I'm so happy today. So, where did we study last time? What topic did we chat about? Let's have a review, then we go on to today's topic. So, I like a lot of volunteer. So somebody help me. Last lecture.
We were talking about the Flory-Huggins Theory, looking at a polymer solvent mixture.
Right.
Looking at the entropy there.
So we start from Flory-Huggins theory. Actually, before that, we talked about lattice theory, which is more generally applied to any material. In a binary blend system, I think it was very fun to count again the statistics. What is entropy contribution? Right? We did a counting on the board. We draw a lot of nice looking lattice. And we give an example. What is the entropy contribution for the material system? Okay? So everybody knows entropy favors mixing. If entropy doesn't say no, entropy is always say yes, we're going to mix. Okay? And we also discussed about enthalpy contribution for the last class. Enthalpy contribution is a little bit more complicated because we need to consider molecular interaction between different parts and how they actually come into play, right? And instead of worry about molecular A versus A interaction, we actually introduce a new parameter called Flory-Huggins parameter, which summarizes the changes in the interaction before and after mixing. If everybody recall, interaction parameter 1, 2 minus half of 1, 1 minus half of 2, 2 is actually directly related with this chi parameter. And eventually we discuss the end of it is what is Flory-Huggins series for a blend system, right? For a polymer is involved. And that comes into this very famous person. Is my idol, probably like the superstar like Justin Bieber's for you guys. There's another handsome guy we don't have place to show called De Jing, is also very famous for developing the scale theory, okay? Flory, he comes from nowhere. He just has a pen and a white piece of paper, and he started thinking, drawing equations, and he was able to develop this called Flory-Huggins theory, okay? So he basically says or predicts that delta G for mixing is going to be related to the entropy contribution from volume fraction of this is the solvent contribution, phi 1, okay? Volume phi 1, phi 2, divided by n. N is degree of polymerization. And log in phi 2. And multiplied by plus phi 1, phi 2 chi. And chi promotes mixing when chi is less than 0, right? When chi is negative, the system always goes into mixing phase.
So who's Huggins?
Do you remember who is the second one landed on the moon? Second person? You don't remember because all the credit goes to Neil Armstrong. So I don't know who the Higgins is, to be honest.
Buzz.
You know?
Buzz Aldrin.
Good. But, sorry, I don't know. I only know Neil Armstrong is the first one. And I don't know how they decide who's going to step out first. Maybe they throw a coin, they never tell the story. But my point is, I don't know the second one. But Paul is probably a leading figure back then time. And he's well known for his development. I'd better look that up. It's a little bit embarrassing. I don't know what Flory-Huggins theory and who exactly Higgins is.
Maybe his grad student.
Could it be?
Couldn't be.
Could it be, but I doubt. All right. So this particular equation is so important. It's as a cornerstone of the polymer thermodynamics for more than 5 decades. So it's one of the key equations. All right. So everybody have any question for it? Because we're going to use it quite extensively to discuss 2 of the application. One is how do we use Flory-Huggins theory actually to understand osmotic pressure, which is a key topic today. Okay, we're going to talk about how can we understand osmotic pressure for the polymer solution. And second is predict the phase diagram. This will be the class for next Tuesday. We're going to talk about phase diagram. Anything? Anyone? Okay. No, I mean, question about Flory-Huggins theory diagram. Perfect.
When
Yes?
you say osmotic pressure,
Mm-hmm.
are you talking about that pressure has an impact on the entropic or enthalpic contribution?
Oh, good question, good question. Be patient, we haven't touched anything yet. But by the end of today's class, you will know how does osmotic pressure relate this Flory-Huggins theory. Okay?
Mm-hmm.
Since the projector is working, let's check. So keep in mind that that parameter describes the binary mixing. There's a homework asked for ternary mixing. So get ready for that. This means, binary means you have to consider exact identity of 2 species. you just don't have a chi parameter for one material. This means you cannot look at chi parameter for polyisoprene. It has to be matched with another material, or polymer, or solvent, or whatever you want to have it. And it's very much is related to specific structure. It has cis trans content need to come into play, and temperature come into play. And chi is related to the temperature, as we will discuss just in a second. And chi parameter is actually will be the key, as I mentioned, because entropy is always favorite mixing, so chi parameter will be very important. So if you look at, if chi is negative, that means mixing is always promoted, or 100% you're going to mix, okay? Chi is positive, that means you need to have balance out from entropic or entropic effect, but mixing is opposed due to the chi. But to what extent it will need to be evaluated, which has stronger contribution. We did an example in the classroom last time. We showed what is relative magnitude in terms of entropy and entropy contribution with respect to the chi, okay? There is adage saying, like dissolves and prefers like. This is frequently true. So most of the chi values thus is sort of positive, because if you mix in two materials, they are not the same species, they usually entropically are not going to be favored the mixing. I'll give you examples. Example is here. This may be a little bit hard to see. Let me see. I can zoom in. That's nice about touch screen. So where you now can look at several examples of chi parameter. Okay, so this is I believe this is basically, it's a little bit chopped off, but let's take a look. For example, here, polybutadiene on the left in the top. So you can look at polybutadiene with different interactions with solvents. First row is temperature, okay, different temperature. Second row is basically volume fraction, and last row is the chi parameter. So if we look at the specific value here, you can see for polybutadiene with variety solvents, the chi parameter is usually larger than 0. You have value about 0.3 up to 0.6. So relatively speaking, chi is basically, the larger means there's more unfavorable interaction. And on the relative scale, chi is typically on the order of 1 to up to 5, 4, 5 is possible, but most of them are around single digits, so between 0 and 1. And this is an example that everybody can look it up. What is exactly a chi value? This mostly list is polymer solvent. So when you need to look at polymer, you need to do one layer of conversion. Okay? This is a chi effective. The display looks like, doesn't like the number here. So chi is actually a parameter depends on temperature. Chi, what it equals to A is a constant plus B divided by T. Okay? A is usually negative, but B can be positive or negative, depends on relate to the packing. If you plot what is chi versus temperature, then you can measure those. For example, here I cropped another table, listed some of the chi parameters for some of the material. So let's take an example. D means deuterate, okay? DPS/PS means if we mix the polymer of deuterate polystyrene versus polystyrene, you would have A is just a constant, as I mentioned. B is this value, and T is the temperature range it's plot. So if you add the temperature value there, you can actually directly calculate out what would be the chi at a given temperature. So if not given any suggestion, we just say at room temperature, what would be the chi parameter for your material. And you can see polystyrene, same material, except it's deuterated. So there's little dependence on the B, and the value for this material is closer to 0. There's not a lot of specific interactions, okay? But if you look at other polystyrene, PMMA, they will be different. And you can put in a temperature and calculate what the chi is. It will be some value between 0 and 1. Okay? We will come back to this topic again in chapter 7.7 to discuss more detail what exactly chi is. So I'll leave it like this. But as you can see, there's a lot of assumption we give into the chi. For example, we don't consider lattice size difference if we have solid molecular and polymer monomer unit. In the lattice theory, we just assume everybody occupies the same volume. But in reality, you have someone going to be heavier than the other. That comes down to today's topic. What we're going to talk about is osmotic pressure. And anyone have any previous experience what is osmotic pressure is and how our life is related to osmotic pressure? Sonia?
With the flow back and forth osmosis, right? And if there's a buildup on one side opposed to the other, would have a higher osmotic pressure on that side.
Sort of, yeah. So I'll give you an example in more detail. So if you look at here, this is a kind of imaginary chamber. Think about this would be the water. A large tank where in the center of the tank, if we can put a membrane which can allow the water to move back and forth. So it has holes in it. Water can go through, but then not the polymer, okay? So I put this layer of membrane here. Here has water, here has water too. Now I start to add a little bit of polymer in there. What's going to happen in this particular case is because of this presence of polymer or salt or other material, your chemical potential for the water on this side or other side will be different. I'll explain in more detail. This difference causes your water molecule won't be equalize the free energy on both sides, or chemical potential specifically in this case. How does it do that? So it will migrate itself through this membrane and reach the other side. And this will result a pressure rise. And eventually they will be equilibrated because this pressure has contributed to the system in terms of free energy. Okay? So in other words, you would observe the capillary would raise by delta by a pressure of osmotic pressure. We actually rely on it dramatically these days. This is a great phenomenon. Anyone have any clue how we use osmotic pressure?
Fine molecular weight.
Yeah, fine molecular weight is important. Purified water is more like a major application these days. If you have the water goes this way, we call it a forward osmosis because it's a spontaneous process. If you have a concentrated polymer solution, you do dialysis, you put in there, and you keep stirring. The small molecule will go out to equilibrize, but you will have water comes in the other side. Same for osmotic pressure that always drives the water molecule to mix in. If you don't have this membrane, eventually everything will be equal, right? Then there's no concentration gradient or chemical potential difference from solvent. So reverse osmosis is quite simple. Since you can have an osmotic pressure difference, this is spontaneous, but can we drive it reversely? Reverse means we don't want water to diffuse this way, we want water to diffuse backwards. There's actually a way, as mentioned, it's called reverse osmosis membrane. They put a membrane, they put a high pressure pump to kind of squeeze the water molecule there. Of course, you need to fight osmotic pressure and other energy of mixing or entropy of mixing, but you can actually drive to create pure water there on the other side, which apparently is one of the major reasons somewhere like Israel they can get fresh water. They just draw the water from the ocean and get it down. It's not a problem in Mississippi. We never worry about we have a drought except this year. There was one day I was driving and I heard there's a ban, probably 2 weeks ago. You do not allow us to set a fire or burn anything outdoor because of potential fire hazard. You can still do grill. I think the governor will be thrown off the chair or his job if he bans everybody from grill in Mississippi. Not gonna happen, right? But the point is, we're never short of water. However, in California, before I just moved here, it was a record drought. And there's one favorite place we like to go in Northern California called Lassen Volcano Park. And through that, we drove through part of California. You can see the lake bed really drops by at least 20, 30 feet. It used to be where a lot of boats, but now all the boats are squeezed in a tiny pond, right? And they have started adopting similar technology to make reverse osmosis to create water, okay? And I think this is only going to go worse because a lot of area in the United States as well as outside the United States is heavily water stressed. There's less clean water people can access to. It's a little bit off topic, but for the polymers, what critical is how can we take advantage of this osmotic pressure to understand polymer property? And that's the whole topic of what we're going to talk about today is how can we understand this phenomenon? I think everybody should know, right? You all read the chapter 7.4 and it tells you what is osmotic pressure depends on the concentration of the polymer and molecular weight. Everybody gets that? So we will explain to you actually why we can predict and understand dependence of molecular weight as well as the concentration for material. It's also important that there is, by measuring different concentration of our polymer, we can actually understand the solvent quality with our respect to our polymer. Did everybody remember we have discussed good solvent, bad solvent, theta solvent? It's one of the major themes in the first chapter. So for today's lecture, for the first time ever, we would be able to tell you how to measure a theta solvent or how to get a theta solvent. Okay? So let's get on to this. Anyone has any question about what's the phenomenon for osmotic pressure? All right. Oh no. I hope it will come back. Hold on. it's really annoying. Okay, I'll get a new cable in the break. So we're gonna start the discussion from the change of free energy. Okay, so this discussion starts from the thermodynamics. When we talk about in the first class, if you look at the equation here, the dg is gonna be having dependent on S. S is the entropy, dt, V, dp. V is the volume in the system, and P is just a parameters talk about the pressure, related to the pressure, okay? And the last term, this is important because this is related to the osmotic pressure. First is chemical potential. Mu I is chemical potential. D and I is partial molar volume. Okay? Everybody gets this? So if we take a partial derivative, think about if we take d free energy, take a partial derivative for T, because the pressure, volume, free energy, they don't have any component related to the T, so you would naturally get this relationship. Delta G, partial derivative of temperature, will be minus of the enthalpy of the system. If you take partial derivative related to pressure, you're going to have the volume. And last part is if we take a partial derivative in the molar volume, I, here, you would have the mu I, which is chemical potential. Okay? And this is just a review of what we did in the first lecture, in the review of thermodynamics. And as you can see, because this is independent of order of differentiation, so we can take a second derivative of mu, this parameter, to P, and basically can be related to all these parameters what we have to talk about. Everybody following this part? What is this? If you take a second derivative of G with respect to the pressure and molar volume, this will be first the derivative to the molar volume will translate to a mu, and second derivative will be related to P, right? This looks a little bit quiet than before. Thermodynamics.
You said you take your first derivative with respect to mu.
So let's give me 1 second. If we know this partial derivative for this will be related to this is molar volume, right? This is chemical potential. So if we take second derivative of G with respect to Ni, molar volume, and together with pressure, this basically can be separated as you take the derivative twice, right? If you consider this, first derivative will translate to mu I, so a simple mass transformation. Okay? And all these parameters are interrelated, because if we take partial derivative to the P first, what do you go get the volume? In other words, if we want to consider free chemical potential, partial molar volume, they are somehow interlinked. and the interlink for the system is given by here. And it will make an impact. Okay? Why? Because in here, the display is again messing up some of the equation. But again, if you look at partial molar chemical potential for the left side of chamber, basically for mu1, when we consider a solvent, okay, let me show you. This one is related to the solvents. This is the left chamber, okay? So this is on the left side, or show us here. The chemical potential when the system reaches equilibrium says, my left will be equals to right. Right side is where we have a polymer, right? So that means your chemical potential on the left is a pure solvent. It's going to be just a chemical potential mu1 0. On the right side, it's going to be mu1 related to P0 and plus osmotic pressure difference. Got it? And we can further expand this osmotic pressure to be osmotic pressure plus partial volume. This is V1, as shown as here. That's purely thermodynamics discussion about what is the chemical potential on the left and right. So now, one of the things we need to understand is now the free energy is related to a dimensionless number, which is given by the equation here as a very low pressure, as we highlight here. So on the left is basically plotted as pressure. On the right, again, is pressure. In the ideal gas, they would follow totally linear line. But for the real gas, they will show a slightly difference. So if we rearrange this one, go back to the equation here. So if we rearrange this, pi V1 would be equals to this term minus this term, right? And which we show in the bottom here. Your chemical potential in the left chamber minus chemical potential on the right chamber with respect to the solvent is going to be your osmotic pressure multiplied by V1. Mark.
V1 is partial molar volume, right?
Right. Partial molar volume for the solvents. And 1 is always going to be the solvent. Okay? And it is linked to minus RT ln A1. A is just a dimensionless number which is related to the X1 is a molar fraction. Remember what we defined? X1 would be equal to number of molecular 1 plus number of molecular 2, right? In the mixing case, that's just. So all the magic is basically happened in these slides where we have osmotic pressure now is linked to ln X1 is basically your volume fraction for the solvents. So in other words, how much osmotic pressure raise in this tiny circle here? Right here is very much related to what is the volume fraction for the X1. RT is just some constant and dependence on the temperature. Everybody understand this part? If we understand this, then rest is easy. It reminds me like cooking at home. This is like getting all the dishes prepared, and rest is just dump into my slow cooker, then press 10 minutes, then I can walk away. So Ravi.
How do we get the equation mu1 naught minus mu1 is equal to minus RT and mu1?
So this is related to particularly this equation. This is let me try to explain this again. I'm not very comfortable for this particular one, but this basically says the free energy for the system will be at relate to where its initial state and relate to dimensionless number, which is how much volume fraction it has in the given system. So it's a dependence, it's a deviation of free energy when you have different molar volume of your given free energy in terms of being diluted by another species. But this would be the key, because if we could reach out to this step where we basically talk about free energy for the solvents on the two-sided membrane would be related to osmotic pressure, okay? Chemical potential. All right, now, do we know what is X1? We know. We know exactly how much we put in terms of polymer and solvents in here, right? We know exactly what is X1. So we can convert X1 and convert that to a parameter we know. The other thing that we want to do is we want to get rid of this log X term. We have been doing a lot of Taylor expansion, if everybody recall. So if we have X1 would be equals to 1 minus X2. And if X2 is very small, which is the case here, we could expand Taylor expansion. Everybody remember this? Nobody? Right? Correct? Correct? So, if we check back this very simple equation, we know osmotic pressure multiplied by partial molar volume. Do expansion there. Okay, so that means we can divide RT to the other side of the table, which means we only going to leave with X2 plus minus This is very interesting because we now established a really critical relationship for this whole lecture. Constant osmotic pressure will be proportional to X2. What is X2? What is X2?
Is that your mole fraction of your polymer?
Yes. So how much polymer in the solution, right? X2. And I can just call these as a constant called a B. B is just a constant I given to it. We're going to define what's the name for B just in a moment. We can also, why don't we call another one C? osmotic pressure depends on concentration of your material. It's not exactly concentration, but related. This is molar, this is a volume fraction, okay, of your polymer. Higher order dependence, even higher order dependence. But we know X2 is typically between few percent. Everybody agree? When you dissolve a polymer in a solvent, you're going to have very little at low concentration state in this particular example. So in the low concentration, your osmotic pressure is dependent linearly on X2. Or I would say it, we can do a little bit of trick, convert this to the concentration. In this term, X2 squared will be much smaller than X2. So we don't even need to worry about X3 because this will be tiny, tiny, tiny. So we only need to consider these two. Or a lot of time, you would be plotting. Don't jump that much. Do it slowly. If we divide X2 here on both sides, you would get this will be equals to 1 minus bx2. Oh, we can use plus. B is just a constant, okay? This you're going to learn for about at least 2 weeks next semester. Dr. Simone will tell you all about it, okay? But I'll tell you a little bit more. If we plot osmotic pressure with respect to the concentration, you will be able to determine what is B secondary viral coefficient, and this is very critical. So big picture wise, everybody understand how does osmotic pressure depends on different volume fraction for your material? Sonia, please.
When you say, I think I'm confused about which one is the concentration. And is X the mole fraction and then C is the concentration, or is X considered concentration?
X is not concentration.
Okay.
We're going to spend a couple minutes to talk about that. Since you mentioned. So what is X? So X is mole fraction, which is related to N1 plus N2. What is N? N1 is mole of solvent. N2 is mole of polymer. How does concentration relate to N? Concentration, C is concentration. Okay, this is going to be fun. Concentration is weight divided by volume. You got grams per mil, right? That's your concentration. How does it relate to N? San. How does your concentration relate to N? Okay, so you need a volume, right? Yeah. You need to know number of moles, so which is, could it be N2 multiplied by molecular weight? Everybody understand? This is very straightforward. Number of moles, molecular weight, you have total weight of polymer in a given volume. That's your concentration. Now, how do we link X2 to C? We should not write C2 because this basically means concentration for the polymer, okay? So, we come back here, X2 right? We know N2, if you link the other way, N2 will be equals to C multiplied by volume divided by M. So let's put it in. How about N1? That's a molar for your solvents, right?
That's the 1 minus x2.
Yeah, that is 1 minus x2. But how many moles of solvent? In this particular case, we're going to take advantage of one definition we defined in the chemical potential, that is molar volume. Okay, that means how much a mole of solvent would take up a certain volume. So this basically, if we know, again, this is volume of the whole system. This is a molar volume of the solvents. This, by definition, is related to 1 moles of your solvent equal to a given volume. So if you divide these two, it's going to be your moles of your solvents, right? All right, we're going to do this one more time. For the other part, N2, if you do a simplification, the simplification is basically our N2 is much smaller. If you're given that simplification, we can basically eliminate this part. This only works for sample is very small. So this gives you, how does X2 relate to the solvent concentration? How does X2 relate to solvent concentration? So look at this equation again. X2 equals to C, concentration of our polymer. V1, molar volume of our solvent, constant. M is molecular weight of material. In other words, molar volume fraction is only going to be, is almost proportional to concentration, except that we need now consider the molecular weight. How does it come into play? Right? So if we do one more thing, if we plug into this particular equation, we would be able to get another way to write the concentration of our material system is going to be, so this is pi divided by concentration RT will be inverse proportional to molecular weight plus B multiplied by concentration plus some higher order term. And this B and is not the same as this B prime, but they both are constant, okay? Not exactly the same because they would be dependent on V1. Okay, any questions so far? Mark?
To find the moles of your solvent, you divided the total volume by the partial volume.
Yes.
Does that assume that there is no volume contribution from the polymer?
We basically made assumption. We didn't say there is no volume contribution. We says this volume contribution is small, so we kind of eliminated that. And in the dilute solution phase, the volume of the polymer will be relatively small. Think about 1% of solvent. How much? Okay, so what this equation now tells us, the most important one for today's lecture, I'd better show you guys also on the slides. This basically says, well, osmotic pressure divided by RT would be equals to x2. It's a little bit messed up. x2 divided by V1. V1 is partial molar pressure plus A x2 squared. This is the first relationship we actually developed here. Okay? And there is a second. This term is basically A is related to second viral coefficient, and is basically constant. Let's go on one more slides. It will show you what we just did there. We can relate what is x2 related to. x2 is a partial molar volume fraction and concentration. Straightforward, right? Here is one of the key conclusions for today. Osmotic pressure divided by RT, as we see many times, will be related to this particular equation. Okay, pi, or I should call it osmotic pressure divided by RT will be equal to concentration divided by molecular weight plus A2, and this is what we call the second viral coefficient. And A2 is important. If I ask you, we're going to take a break, okay? Just after this short question. If I ask you, if I have an undergraduate working in my lab, he's very interested in a simple project, I asked him to, what if you measure my polymer, measure osmotic pressure, you just make the polymer solution. There's probably an instrument you can put it in there, measure the osmotic pressure, just read how much height is raised. Height can be related to the pressure. So he measures concentration for our material C at 1 grams per mil. You got C1 and C2, 5 grams per mil. You got the second osmotic pressure, and this goes on. And if he plots osmotic pressure divided by CRT with respect to concentration, should I expect a linear relationship in this way, or it will be flat, or this way? We're going to take a 5 minutes break, and I want you to tell me which one you believe. If this undergraduate is doing the experiment right, based on what we talked about, osmotic pressure divided by CRT is going to be a upturn, a flat, or downturn. 5 minutes break. We'll be right back. Okay. Lena, you got a really bad angle.
No.
I know. I need to keep.
I'm gonna go look at it.
Yeah.
Because I was,
Very much so.
yeah, and now like all of the numbers kind of miss mass, so I don't know which
Oh. Okay, let's get back. Okay, Sonia is the only one missing. Let's give her a few minutes. So we're gonna do a vote because we're in the United States. We're gonna have 3 candidates for this year's president campaign. One thinks he's gonna bring all the economics up. B thinks I don't need to do anything. I want to keep a status quo. C thinks I want to drop unemployment rate low. Which one is right? Which one you would vote for in this particular case? So somebody thinks osmotic pressure for this unknown polymer versus different concentration will go up. Come on, shout out for A. No one? No, raise it higher so I can see you.
It's high.
Be proud.
So we have most of people here. Kevin, you as well? Okay. Oh, we don't have much left. We have only some of the other people, okay? How about anyone thinks the osmotic pressure will not dependent on concentration, it will be flat. So the student makes 1 mg, 5 mg. When he measures, this will be not flat, but divided by concentration, it will be flat. All right, remember, Lena, there is a C here.
thank you.
Okay, how about it's going to be flat?
I want to vote for all 3, so I'm not wrong.
No, you can only vote once. I saw Levi. How about someone think it's going to be the case C?
Clearly the wrong answer, but I'm going to take it. I'm aware.
So you're the only at C. All right, everybody want to know?
Yes.
I think everybody is all wrong. It's not A, not B, and not C. It depends. It's all possible. It depends on what polymer you put in what solvents. All could be all wrong. So, let's talk about this case. If we go back to this very fancy equations, if we do a little bit of arrangement, CRT, pay attention to this concentration term. Going to be equals to, somebody help me? 1 over n plus A2C and BC. They're basically saying, okay, don't worry. This is just called second viral coefficient. It's a constant. So now, this basically becomes y in this plot, right? This is the y-axis. What is the x-axis we are plotting? C. So this doesn't depend on concentration, so we just, it's a constant, right? Then plus A2 plus C. So in the case A, A2 is larger than 0. Agree? You would have a positive term, a positive dependence on concentration if your A2 is positive. A2 is almost 0. Then this undergraduate student would measure and plot the data as almost a flat, as B case. Everybody agree? How about C? This would be related to solvent strength. Do you have another way to say it?
Like your compatibility with your polymer,
Solvent quality, right?
like good
Right. Right. That's exactly right. So this is the way you directly tell your solvent interaction with your polymer. And you guys probably can guess this. Case A, good solvents. Case C, poor solvents. Case B, why this is a Seda solvent?
Is that the ideal?
Because there's equal repulsion and contraction. They cancel each other out, of course.
It will linearly depend on concentration, but not, if plot this way, it will not depend on other part.
I'm not sure, but it's positioned because it's equally avoiding everything.
Right. So in the Seda solvent, the polymer don't condition because your interaction with yourself is sort of screened out by the effect of neighboring chain. So your chain itself is behave like Gaussian chain. So in the Seda solvent condition, your osmotic pressure will go up with concentration, but it will not go up, will not speed up because this A2 turn is 0. Okay? But pay attention that if we plot this osmotic pressure divided by RT for C, we don't divide, okay? B is going to be linear. So if you measure a concentrated solvent, your osmotic pressures will always go up. But we want to understand how fast it go up, which is in this ABC. Okay? All right, we kind of already show here. If A2 is positive, it will be, the chains will be expand. A2 is negative, that means it's a poor solvent. Okay? And secondary coefficient is basically strictly coming from the interaction between one polymer chain, which is very small in most of the case. It won't influence the results, so we only need to consider two terms. As you can see, C3, C dependence power of 3, if it's in very dilute solution, this term is minimal. All right, we have one thing haven't talked about is how does this relate to Flory-Huggins theory? This is just generally how osmotic pressure is related to concentration and how we can get second-order coefficient. And we will take a look of what it is then. So before we do that, we're just going to emphasize one more time. A2 equals to 0, going to be the Seda solvent condition. Okay? And here, if we dig a bit, you can see what is Seda temperature and solvent for various material. It's pretty randomly distributed, but you can think about polystyrene, cyclohexane. In real world, we don't worry too much about these because we never would ask a student to make a Seda solvent polymer solution. Okay, so I think we also covered this. We just need to discuss one more time. This is also talked about. If we plot osmotic pressure divided by CRT, the intercept with Y, this tells you it's reciprocal to the molecular weight. This location where it intercepts with the y-axis will tell you what's the molecular weight of your polymer. Okay? The slope we already talked about, it's A2. A2 is the secondary coefficient. It will tell you solvent quality. But because you cannot measure what is concentration at 0, so this point you were never able to get. But you can measure this point. this point, this point, this point, this point, then make a linear extrapolation. And this would be intercepted with y value. You can read your axis and get this value and convert to the molecular weight. In reality, don't use maser. It's not that particular accurate, and light scattering is way easier to measure the molecular weight. It can be used to measure it, but it's not popular these days for a professor to ask the student to measure osmotic pressure to get a molecular weight. Okay? All right, we don't need to discuss too much about that. So this is several experimental data I just want to share with everybody. So this now plot is osmotic pressure, which is unit should be ATN, and horizontally it's the concentration. And everybody remember what is unique about polystyrene in cyclohexane? What is unique about this? Theta solvent at 34.5 degree. So this is theta solvent. And if you this would be increased more rapid than what is basically unfilled square symbol. This is a theta solvent. So if I have to draw a line, and let me try. Pretty good, huh? This is basically the theta condition. If you have a linear increase in terms of concentration versus osmotic pressure. And remember, this is not plotted as CRT. This is just the osmotic pressure. Of course, RT is constant. Okay, that's the difference. So if it's above there, means those are what solvent? This is a good solvent, right? Because it's over, you would have, if you plot pi divided CRT, it will be curved up. Your second viral coefficient have a positive contribution in your osmotic pressure, okay? And low temperature is negative A2. Or not so good solvent, okay? And if we take the same data and plot this way, that's what we talked about. Not plot directly osmotic pressure, but divide by concentration. This is what you would have. And this almost near horizontal line is suggesting this A2 is equal to 0, or theta solvent. This A2 is larger than 0. This is A2 smaller than 0. Experimental data. Okay? All right. So one little topic we need quickly touch base is A3 contribution. Three-body contribution. It only happens at a very high concentration. As I mentioned, if a C goes up, then we cannot eliminate higher order term in terms of concentration. It will come into play. Okay, and as this is plotted again, osmotic pressure dependent on C, and you will see the data is not linear. You can see it's quite significant, will show upturn at higher concentration. Especially in the data is non-linear, then you need to really worry about that. Because pi divided C plot to C should be linear. Right? Any question about this part? Okay. But most of the case, we wouldn't need to consider that. So Ravi, you look very confused and want to ask a question. Say that again?
Why is the y-intercept changing?
This is not the same material. Even for the same material, it would intercept different if you have different molecular weight. So for two different reasons.
A3 and A2 and A3, they're all different things.
Yeah. But the point I want to show in this slide is, in the previous data, we would expect a linear line. Good solvent, theta solvent, or bad solvent. But it should not have a data shows nonlinearity. It will not show this, then start to speed up or deviate from a linear one. It's only could be possible if we consider a third term, which is called A3C squared. And you can see C squared would follow a nonlinear trend. Right? Okay. I don't think I need to get into relation to Flory-Huggins theory today. We covered quite a lot. So I'll take a break from here. Then next class, we're going to start just a link to Flory-Huggins theory. And what I can tell you is those two methods or description are the same. There's a parameter called Flory-Huggins parameter, and there's a parameter called second divisor coefficient, and they happen to be describing the same phenomenon. Okay? And take-home messages, please go home, take a study of the first 3 chapters, and we will have a short quiz in the next class. Okay? And I'll assign some of the homeworks starting next week, starting next class. All right? Okay. It is chi. Chi and A2 are related, and we haven't got time to explore that part yet.
Do we have to have equations memorized for quiz?
We have a quiz sheet, equation sheet. You already see it. Yeah.
Nice.
It's the same equation sheet. It's going to be the same for your cum exam.
Great.
Mm-hmm. Mm-hmm.